Okay, here we are in our notes, polarized and unpolarized light. We've already talked about all this, two types of polarizations. You can have what's called, this is polarized light. If it's oscillating kind of at an angle, or even at this angle, those are still polarized. So what are they? They're linearly polarized, but they're not horizontally or vertically polarized. They're linearly polarized at an angle. Okay. And we said also we can think of light as photons. Photons are the minimum amount of light that you can produce, which is kind of weird. There's some minimum amount of light that's capable of being produced. And the photon is that minimum amount. So if you have unpolarized light, you just got a bunch of photons, and they're all at different oscillations or different directions. And in the next moment, they all switch. You know, this guy down here, now instead of horizontal, now he's vertical in the next second. And this guy changed to maybe horizontal, or maybe he's at an angle, right? They all kind of vary randomly. And this one, maybe this one's just a little bit different. And at every moment, every single one of these is just changing randomly. So let's get some IB definitions. Here are the IB definitions for polarized and unpolarized light, the descriptions we might call them. Polarized light. And you gotta copy this down. Let's make it a different color so you know to copy. Polarized light is light where the electric field always oscillates in the same plane. And unpolarized light is light where that direction of electric field oscillation is constantly and randomly changing. Those are the definitions. If I ask on a test, right, state what's meant by polarized light, you state this. If I ask what's meant by unpolarized, you state this, the second part. Maybe I can get this on two different lines. Let's go smaller. Okay. Even when the electric field vector is linearly polarized, but at an angle, let me draw it. Ooh, at an angle. You can still break the light into components, because that's what we like to do. We like working with horizontal and vertical. So let's break this bad boy into components. Whoa! Break it into components. You've got some X, that's not really on the X-axis, X component, and you've got a Y component, right? A Y component, but wait a second. Wait a second. We could draw those Y components, we could just slide those over, right? Let's try that. Let's take our unpolarized light. Unpolarized light. What makes it unpolarized? Oh yeah, it oscillates in every single direction. So when I draw this, I'll make every single direction. Every single one will be in my picture. Well, maybe not every single direction, just a few. But you could imagine there's more arrows. You could draw this arrow, and just drawing arrows forever. Right? This is a 50-minute video, and 40 minutes is occupied by drawing arrows. No, please don't do that. We'll just draw a few. Every one of those angled arrows can be broken into components. So let's break them into components. Here's one component, here's another component, here's one component, here's another, here's one, here's another, here's one, here's another. Okay, and because I've drawn these as components, I can get rid of the original two-dimensional vector. Whoops, let me move the components over. I'm getting rid of the original 2D vector because I don't want to represent it twice, I just want to represent its components. Okay, but look at this. I take this component and I stack it on, I add it up with the existing Y polarization. And I add this to the existing Y oscillations, I should say. Right, these arrows represent oscillations in the electric field strength. Okay, and so I add the X's as well. And look at what I have done. I started with every possible direction, and I ended with just two directions. So we can take this picture here. Oh my gosh. Drawing with your mouse, not always a great idea. You can convert it to light which is just vertically and horizontally polarized. So let me take away the original. These two are equivalent. Both, in fact, represent unpolarized light. This is unpolarized light, and so is this. Okay, clear. Makes sense. Okay, on to polarizers. A polarizing filter, filter is a fancy device. It's also called a polarizer or Polarized. It's a device that only transmits light whose electric field oscillations are in one direction. So look at this guy down here. This vertical line tells you, hey, only vertically oscillating electric fields get through this filter. And all of these others, what happens? The others are absorbed. Horizontal light is absorbed by the filter. Absorbed. Now we can draw this same picture by, instead of showing all of the different oscillations, just show the components, right? That's what we did up here. They're equivalent. And sometimes the filters are square, sometimes circular, and only the vertical gets through. You can think of this line here, think of it as like a window, and only the stuff that can pass through the window will make it through the other side. The horizontal can't go through that window. It's not the right shape. Okay, so what is this line called? That line right there is the transmission axis, and it indicates to us which direction passes through. Okay, next page. So let's take a more complicated scenario. Let's say that our light is vertical, like this. Or no, you know what? Let's make the light, let's take a complicated situation. I said complicated, didn't I? It's at an angle. Uh-oh. Dun dun dun. And the filter, here's my filter, has a horizontal axis. Wait till you see what happens next. It's like a YouTube video. I'm trying to trap you into clicking on the link. What happens? Some of the light gets through. But how much? It's a natural question, right? How much gets through? If you have some angle. Well, the first thing we have to consider is, okay, how do we define this? The filter, I'll do this in blue. There's the transmission axis. Let me make the polarization plane in red. We'll use red. Here's the polarization plane. Whoa, that's not the angle. It's like this. And the angle between those two, that I will do in black. That angle is theta. Theta is the angle between the transmission axis in blue, the polarization plane in red. So there's some original intensity before the light hits. There is some original intensity which we call I sub 0, and after it goes through, there's some transmitted intensity which we just call I. What's the relationship? You might be able to guess the relationship. Here's the transmission axis, right? Let me draw that axis as a dotted line. Here's the oscillation, and here's the angle theta, right? Theta. And look at this. The blue line is really showing, well, okay, so sometimes we start out like this, and then the field grows to this, and then it grows to that, and then it gets smaller, and it goes back the other direction, right? That's what the blue line is showing. So it's showing the amplitude. And of that amplitude, only this part, which is parallel to the transmission axis, remember? The transmission axis is this blue line which is horizontal. Only the part parallel to the transmission axis gets through. So this part is A cos theta. But wait, what's the relationship between intensity and amplitude? Intensity is proportional to amplitude squared. So their ratio is a constant. The original intensity, don't write this, no, you can write this down. The original intensity over the original amplitude squared is equal to the transmitted intensity over the transmitted amplitude squared. And what's the transmitted amplitude? It's the original value, AO, AO, the original value, AO, times cosine of theta, right? Here's the original value, and here the cosine component is what gets through. So I'm going to write AO cosine theta. And if you take this and you simplify, what do you get? You get the transmitted intensity. I can leave this as an exercise for you. Is the original intensity times the cosine squared of theta. This is called Malice's Law. One of those fun words where you have an S apostrophe S. Oh, those are so much fun. Yes. Oddly unsatisfying, isn't it? Okay, I is the transmitted intensity. IO is the original or the incident. We call it the incident intensity when the light is originally incident on the filter. Intensity. And what exactly is the theta? Well, look back up here. It's the angle between the transmission axis in blue and the and what was the red? The red was the polarization plane. So the angle between the polarization plane and the transmission axis. You might write these words all out, right? I'm just abbreviating because I'm writing with my mouse on my computer, and that's annoying. Okay. So, person A, there's no people A and B, just A. Can you use Malice's law if the light incident, this incident light, if it's unpolarized, can you use this law, this equation? If it's unpolarized. Well, look at this. You require the polarization plane. If it's unpolarized, there is no one polarization plane. So no, you can't use Malice's law. Because there's not just one polarization plane. Theta, you can't define theta. Okay. In Malice's law, does I represent the intensity of light which is polarized or unpolarized? Ooh. I. When we say the intensity I, the transmitted intensity, here it is that intensity describing light which is polarized or unpolarized? Well, look back at the picture. What do you think? When the light passes through this filter, is it polarized, this intensity? Is the light polarized, unpolarized? Go ahead and write down an answer. Intensity is perceived by humans like really intense light is something, and low intensity light is something else. It's the brightness, as we already know. Because dark spots have zero brightness, and bright spots have high brightness. Now here's the thing. Malice's law we saw, it only works if the incident light is polarized. But what if the incident light is unpolarized? How much gets through? If you have this scenario, here's the light unpolarized, and it's traveling toward, let's make it simple, a horizontal filter. How much gets through? Clearly half of it, right? Because half of the E-field oscillations, this half, is parallel to the transmission axis. And this half is not going to pass, it's going to be absorbed. So this half, which is parallel, passes through the filter. The other half, we said, is absorbed. So hence, exactly half the incident light is transmitted. Now when two Polaroids or polarizers are crossed, We say they are at 90 degrees to each other. And we know the answer, how much light gets through cross Polaroids? None. Zippo. Okay, so I'd like you to try Malice's Law practice, or maybe I'll do a quiz. I'll let you know.